which was developed mainly by Jean Nicole in 70s and 80s and 90s. It's for many, many years. And it's about the general idea that all functions, all series are secretly analytic. Even if they are divergent, then you can try to find some clever way to make analytic continuation. And the general series is very well involved. And I will talk only about the simplest and the most common class of resurgent series, which appears in many examples. And for this class of series, you have not just one series, but some collection of series which interact with each other. I will give kind of definition of such situation. It's a simple resurgence package, which is the following. It's a finite collection or maybe countable collection of complex numbers, and complex numbers are in what's called Borel plane. I will explain it in a few minutes. So it's complex numbers, but called Borel plane. And for each of these complex numbers, you get a formal power series in a variable, which is not variable on this Borel plane, it's variable on another plane. And at point of view of kind of physics and quantum mechanics, I'll call it Planck constant, although it's variable. So you can imagine it's kind of small number. And so you have a series with complex coefficients in this Planck constant, in H bar. And the main property is that the series will be divergent, will be of what's called Gervais class 1. So what does it mean? That if you consider case coefficients of the series, it's bounded by k factorial times some exponential growing function. So typically series are divergent. Of course, it could be convergent, but typically they really grow like a k factorial. And the third part of data, it's an integer. For each ordered pair of this number z alpha, it's called singularities in Borel plane. And this number is called Stokes index. Yeah, so the main interest for me in the Stokes will be the fact that the Stokes indices are integers, and it's a reflection of certain integrality coming from what to be topology. But we will go to this later. So how all these three types of data, complex numbers, series, and collection of integers interact with each other? First of all, for each z alpha, we can make a convergent series, at least in the neighborhood of 0. Namely, we divide coefficients by k factorial, so now we'll have exponential growth, and consider the Taylor expansion around point z alpha, and coordinates of this Borel plane are denoted by zeta. Now, so we get a function of zeta defined in the neighborhood of point z alpha, many functions. And the property is that if you try to make analytic continuation of any function along any path originated z alpha and avoiding other points, then you will be able to make this analytic continuation along any path. And if you approach one of possible singularities, what you will see near this point, you will have again a holomorphic function plus a function associated to the singularity multiplied by a logarithm and divided by 2 pi I, and maybe multiplied by integer. So what does it mean? That if you go around the singularity, the function will change the value, and the jump will be integer multiple of function phi beta. Yeah, it's actually a mistake, it's beta, not b. Okay. So these functions kind of are defined modular integer combination of other functions. Here in this description, I said that n integer coefficients, it's not exactly n alpha beta, because it depends on the path. Yeah, so this integral coefficient depends on the path, how I approach from one singular point to another singular point. And n alpha beta appears in the special case when you go along straight ray from your point z alpha to some z beta. There are several possibilities. This z beta could be, if you go along straight way, you meet any other singularities. Then this multiple will be an alpha beta. But if you, like on the picture, go to ZB2 or ZB3, you should cross the singularities, and we are not allowing to crossing singularities, so we avoid them by a little semicircle on the right. And that will be the definition of numbers in alpha beta in this canonical way to approach from one singular point to another singular point. Okay. So we see that we have in this description of these integers in alpha beta, we go essentially by a straight race. And what really goes on if you start from some singular point and try to make analytic calculation along all possible straight rays? Yeah, so if we start with some singular point, make calculation of all straight rays, and you will get only, and you go up to the first singularity, and then you make a cut. And what you'll see, you get, you will cut your complex plane by maybe finitely by infinitely many disjoint cuts. So disjoint cuts will be the following. You take some other points and consider all points which lie after this point, if you consider the straight ray. So you get some just discrete subset of points. And also I want to put some points also on the cut, some kind of one singularity is shadowed by another. And what you do, you make analytic continuation static not point from the alpha, but some nearby generic point. And then 6 will be not aligned. And then I go to the limit when this reference point will be close to the alpha. So start from the alpha plus epsilon, epsilon is very small complex numbers, and then take limit. Yeah, so you get this picture for each singular point in this resurgent package. You will see countable collection, not possibly not all, but some countable collection of other singular points, which is discrete subset, and you make this infinitely many cuts, and you get analytic function defined outside of the cut. So what is Borel summation? It's a procedure to associate certain actual analytic function with my divergent series. I recall that my divergent series was C alpha 0 plus C alpha 1, C alpha 2. It wasn't the generating series of phi alpha because we multiply by factorials. And how to reconstruct my actual functions? So it will be no longer have this superscript formal. It will be actual function depending on some domain. You consider a cut. You consider a ray which doesn't go through the cut, starting from your point the alpha. And you make a Laplace transform, integrate along this ray. And when you make the Laplace transform, then monomial will go to the monomial, but then you multiply by integral of z to power n exponent minus z will be n factorial, so recover factorial. So you get the things with the same asymptotic expansion. And this function depends on h bar, but h bar it goes in it's defined not in a whole neighborhood of 0, but in a small sector containing around the ray. So argument of h bar will be close to theta, and absolute value will be close to 0. So you get some like small maybe triangular sector in h bar plane where functions will define. So you get this procedure is called Borelius summation. From you associate actual function to this divergent series. It depends on the choice of direction. If you go different direction, it will be different functions with the same asymptotic expansion, defined maybe in a little bit different domain. Okay, so let's return to this my multivalued function phi alpha. We get finitely countable many multivalued functions which are analytic continuations, and they satisfy some linear relations. Jumps of one function are integer combination of other functions. So you get a certain monodromy structure. You get representation of this all monodromy structure is encoded by Stokes indices. If you go with the Stokes indices for for this almost straight race going from one point to another, avoiding singularities on the right, then I can reconstruct this jump indices if you go along arbitrary path. So monodromy structure is determined by this Stokes indices, and usually, but not always, as you will see, the Stokes indices form a skew-symmetric countable infinite matrix. If the set of singularities is discrete, which is in almost all examples in my talk, essentially, for example, if it's even finite, then we obtain a local system of a complement to this discrete set with fiber which is a finite or countable sum of copies of integers. So it will be lattice with a basis locally. And in general, if my set of singularities is not discrete, which in complicated cases is what happens, we get some kind of more exotic object which is locally constructible sheaf of at most countable free abelian groups, and with some property which I didn't spell it. It's this sheaf has no zero cohomology and zero first cohomology, so it will have vanishing both zero and first cohomology. And this simple resurgence is a homomorphism from this what to be constructible or locally constructible sheaf to the sheaf of holomorphic functions in the Barrel plane, satisfying certain properties, but essentially that what one can formulate abstractly. Okay, so what one can deduce from all the structure? So we get plenty of formal series interacting in some way with each other. So it's easy to see what happens when you have, just suppose have two closest singularities in your set of singularities. There are two of them which has the smallest distance. All other pairwise distances will be larger. Then each singular point will say that your function, if you make analytic condition, will be a logarithm multiplied by something at another point, and it will contribute to the growth of coefficients. And then you can see the following. You get coefficients at expansion of my function at point z alpha divided by k factorial, and multiply the distance between power k, multiply the 2 pi I, because it was some 2 pi I in the jump. And then we get integer number and alpha beta, and then we get contribution for what to be expansion point z alpha of logarithm multiplied by holomorphic function at z beta. And you see the contribution of leading term, next term, and so on. So what here goes on? The leading term in the growth of coefficients at point alpha, the alpha, are controlled by zeros coefficients and expansion at point beta. The next term corresponds to beta 1 and so on. So you see that the growth of coefficients of series for large k at one point is controlled by coefficients but with very low indices in another point. So here there's large indices, here's low indices. And here, because there are 2 points close to each other, you get the same interaction. Coefficients in B controlled by coefficients in A in opposite way. Yeah, so it's, in a sense that can be thought it's what the meaning of Earth resurgence. You have some series, it's divergent. You try to find its asymptotic behavior. You expand in this way. It's essentially like inverse powers of k, but slightly different denominators, but it's equivalent. You get another sequence of number. Again, you see this factorial divergence. You make expansion, and you go back to your original sequence. So these two sequences kind of one uniquely determines another. But what one can conclude from this? Let's consider this leading term for coefficients at the alpha. It's controlled by C beta 0, and here conversely. And then if you just take some product and ratios, you see that you calculate something at point the alpha, not knowing about the beta, only this position of singularities. You consider case coefficients divided by 0 coefficients divided by k minus 1 factorial, because it's k cancels k factorial, divided by ratio of distances, take limit of this, then multiply by another limit, which you calculate point beta. Then the claim you get 1 over 4 pi squared times the square of integer. You get 2 pi I squared minus 4 pi squared, and as I explained, usually n alpha beta is equal to minus n beta alpha. Yeah, so you see this integer is popping out is a product of two independent limits which you calculate for two kind of apparently independent series. Yeah, so it gets a very elementary way to check resurgence when you have two series. Then you can immediately see numerically if they wanted to be kind of correspond to closest 2 points in some resurgent package. You should calculate approximate some limit and get this very high precision square of integer. Okay, yeah, so it was a bit abstract story. What should explain in this integrality? And there is a natural geometric source of this simple resurgence package. It's exponential integrals with more singularities. So we start with a smooth complex variety with some holomorphic function and a holomorphic volume element. And now I'll try to study various things like integrals of exponent minus function divided by h bar multiplied by volume element, where h bars is arbiters, maybe sufficiently small complex numbers, and cycles of integration are non-compact cycles. I go to the direction, they have a boundary in the direction when f divided by h bar close to plus infinity. So exponent will be very, very small. And then one can try to make asymptotic expansions for such exponential integrals. I will go to, in the next page, how to actually get series. It's kind of series in h bar, essentially, of this thing. This integrals, integral of exponent of function divided by small constant are very common in algebra and analysis. So the basic, my first examples will be algebraic. All variety function and volume elements are algebraic. So the first example is a Gaussian integral. So my variety is a affine vector space of any dimension n. Function is this half of sum of squares. Volume element is a product of usual kind of dx1, dxn. And now for, let's say, for positive h bar, we can integrate over cycle of integration with real locus, all real variables. The integrals will be first convergent and get exponent 2 h bar to power n. What series I associated? This actually I should divide in all these examples by this factor n's power of a square root of 2 pi h bar, and here I get just 1. So I get a very stupid series constant 1. It's not even divergent. Then we can consider area function. It's kind of very common special function. You consider one-dimensional line with coordinate x. Function is some cubic polynomial and volume is dx. And therefore you integrate to get area integral. Or if you consider C star, and function will be x plus 1 over x and volume is dx over x, you get Bessel function. And also there is a huge class of examples coming from mirror symmetry, especially for Fano varieties. And if you want to calculate Gromfit invariance for, let's say, for projective space, Pn, it's all encoded in this behavior of these exponential integrals. You take n-dimensional multiplicative torus. Function will be sum of coordinates plus 1 over product of coordinates, and volume elements will be product of dxi over xi, and you get something for which is no standard notation, but it's mirror to Pn. Yeah. Yeah, so I get various situations which such integrals naturally appear. And in all these examples, what happens? At all critical points are isolated in Morse. Morse in the holomorphic sense, because it's a complex valued functions. So the determinant of matrix of second derivative at the critical point is not zero. And also I assume that all critical values are pairwise distinct. But it's not enough. What the third thing which one should assume that there's no, in certain sense, critical points at infinity. Now, for example, there exists a partial compactification of my let's say algebraic variety, extending f to a proper map to complex numbers, so fibers will be compact, such that near the boundary, which could be a divisor, let's say with normal closing, something like this, this projection is locally trivial. So there's no singular points at infinity. Then what happens then for each critical point and generic direction, all except finitely many, we have a canonical homology class integration path. It's called Levshitz symbol. It's a real submanifold defined up to homotopy of this variety X, which is diffeomorphic to Rn. Like recall for Gaussian integral, we integrate over Rn, yeah. So Levshitz symbol is always diffeomorphic to Rn, and it's a union of ascending gradient trajectories for the real valued function. You consider real part of function and you rotate by the face, which you choose a priori it's the direction of argument of h bar. And the gradient trajectory you take using arbitrary Hermitian, not even Keller metric on manifold. So it's very essentially no condition. And it's well defined up to a sign because we should orient it somewhere as a cycle of integration. So how these Levshitz symbols look like? So in the Borel plane, where I take values of my function, it draws a straight ray in direction theta. And the gradient lines, if you use Hermitian metric, so it's compatible with complex structure pointwise, they automatically project to straight exactly to this ray. And when I have this holomorphic Morse function, when I take real part, I take real Morse function of signature nn, when n is the dimension of manifold, and so it will be n minus one dimensional sphere of gradient trajectories which ascend from the point p alpha, and they project to the ray. So you get kind of growing families of spheres. When I approach to zero, it will be vanishing cycle, and together you get Rn, which projects to the ray. And you can integrate your function, exponent of my function divided by h bar will be exponential decay here, multiplied by volume element, which will be only polynomial growth, so the whole thing will be very well convergent. Yeah, so we get this Levshitz symbols, and we, yeah, usually Levshitz symbols considered like classes in vanishing cycles. You consider the only neighborhood of the alpha, but here we make it they're really, really big and kind of infinite. So we define some normalized integral for each critical point as the following way. We take Levshitz symbols going in some direction, integrate exponent function divided h bar multiplied by volume element, but then it should make a little corrections, like for Gaussian integrals. So first of all, the function has some critical value. You cancel this in first approximation, this exponent by exponent plus critical value divided by h bar. So shift value f to have critical value equal to 0. And then you divide by square root of 2 pi h bar to power n, just to cancel this integral for Gaussian integral. And if you get analytic function, and the claim, you get actually many analytic functions because it depends on direction where you made how you draw your ray. So it should be not a Stokes ray. So argument of h bar not equal to argument of difference for some other point z beta. But the asymptotic expansion is the same form power series. You can calculate using kind of what's called weak rules in form power series expansion. And you get the same form power series, and you get actual functions. And then one can easily to see that my actual functions are the same as Borelli summation of this form power series. Yeah, so you see that's procedure to make a divide by factorials, make alternative continuation, make integrals. It actually has very clean meaning for this exponential integral situation. You can say you get this collection of things, these actual functions, and what will be role of the Stokes indices in terms of those actual functions. If one cross the Stokes ray clockwise, then one get a jump by an exponential small term. So you go integrate, consider like directions for Stokes rays, like red direction will be left, and then rotate to get green directions. Maybe there are several groups of points which are aligned in the same way. And now you want to see how this like integral over left stimulus projects to green ray depends, can be expressed through integrals depending on red ray. It's in first approximation it's equal, but because cycles integrations are almost the same, but now you start to compare, kind of go step by step, try to surround these critical values one after another. And then you get exponential small corrections because the jump will be logarithm divided by 2 pi I, the jump will be integer number times another integral. And in this normalization of integrals, you see that you get this common factor which will be the same at all points, and you get exponent of critical values. So this exponent of, when you consider this various normalization, take difference of exponents of critical values divided by h bar will be very, very small positive number. When h bar is or not positive, it will be a small norm complex number when h bar is in certain sector. And then you get this jump formula. So express, you go through one sector to another, and functions will be jumped by, jumps of functions will be linear combination of functions on the left multiplied by things which so small that have no, have trivial tail asymptotic expansion multiplied by these integers. In fact, this is, I think it's a kind of right viewpoint on simple resurgence functions. You don't worry about Borel transforms and integrals. You say that you get just bunch of functions solving this Riemann-Hilbert problem defined in sectors, and get transformation roles to go to the sectors, and that's it. And they have these functions I alpha have the same form power asymptotic expansions, which will be form power series, and that's the interaction between all of them formulated in terms of Riemann-Hilbert problem. Okay, so what are these normalized integrals? If you take any function example, then the critical values are easy to calculate. Critical values, critical points will be something like plus minus 1, and the critical values will be plus minus 2/3. And then you get two form power series in these 2 points, which are essentially the same series, you just change sign of variable. It will be some 6 double factorial product of all odd numbers up to 6k minus 1. And Stokes indices here is calculated plus 1 and minus 1. And similarly for the Bessel function, you get another double factorials, again two opposite critical values, and Stokes indices are plus 2 and minus 2. And that's actually explain why area functions and Bessel functions are so important. It's kind of simplest non-trivial cases. You cannot have a resurgence when you have only one singularity. You should have at least 2. And then the simplest Stokes indices and the skew symmetric is 1 and 2. That's really simplest numbers, which you can imagine. So what is the next example? That's really a new example, not in the textbooks. this is area in Bessel function on kind of most standard examples of researchers, but this next example is not in textbooks, it's very recent, I have to say, maybe 5 years ago. It's a Stirling formula. So my variety is no longer algebraic. It's complex line, but functions exponent of x minus 1 minus x. And volume element is dx. And where the things appears, if you consider normalized integral, as I explained before, exponent minus f divided by h bar, and h bar is inverse to some integer, then what you get factorial divided by usual leading terms in Stirling formula, and the rest will be series starting from 1. It will be asymptotic expansion. So it's 1 plus 1 over 12 plus 1 over 28 h bar square and so on. These numbers are not Bernoulli numbers. Bernoulli numbers appears when you consider logarithm of this guy. You get again series is factorial divergence, and it's very, very well known example in the subject. But without taking logarithm, it's less standard one. This is called Stirling expansion, Stirling numbers. And in this case, the resurgent package has infinite set of singularities. It's infinite set is 2 pi I times integers. And all series, which we have here, are the same series. At any point you get just the same series. This is 1 plus 1 over 12 plus 1 over 28, 288 and so on. So the whole story is kind of translation invariant by this lattice. And let's consider like point 0. Point 0 has two neighbors, two closest points, not 1 plus 2, plus 2 pi I and minus 2 pi I. So it will be kind of like two contributions instead of one in this formula which I explained before. So let me go back. In this situation, when for the alpha, there's only one closest point. But if you have two closest points, you should get contribution for both of them. And here's what's going on for the Stirling numbers. And one can rephrase this asymptotic expansion in the following way. So Stirling numbers know about themselves, but in a very bizarre way. Yeah, so first of all, modify, it's a nice rational numbers by now make transcendental numbers multiplied by powers 2 pi ik, because 2 pi I is the distance between these two closest singularities. So I get, again, some explicit formula, powers 2 pi times some rational, kind of bit ugly rational number. And then the formula is the following. Now consider this numbers as Stirling numbers, modified Stirling numbers tilde for k even divided by k factorial, because it has factorial rows, and the claim that should have expansion which controls by Stirling number, odd Stirling, modified Stirling numbers, but with very small indices like leading contribution for 1, for 3, and so on. And conversely, consider Stirling numbers for odd coefficients, then it has a symmetric expansion controlled by Stirling numbers for small even indices. Yeah, so that's again kind of example of resurgence. If you kind of know one numbers for symmetric expansion, consider another numbers for symmetric expansion, return back to your original numbers. Okay, yeah, so it's very simple examples, and here one easily figure out what are Stokes constants. It's a kind of zeros, plus and minus 1, and some sort of pattern. Okay, so this was some example not long time ago, but then last year we generalized with Jan Sobelman this to a very huge generality. We construct a really huge class of new simple resurgent packages. So the variety of which we make integral, it will be some infinite abelian cover of some algebraic variety. And function, which will be, the differential function will be pulled back of some closed algebraic form on variety, and volume elements also pull back of some algebraic volume form. So where this example with factorial or gamma function comes from? You consider Under algebraic variety will be C star with coordinate y, and one form will 1 minus 1 over I dy, and volume element will be dy over y. But if you consider logarithm of y, it will be coordinates on universal abelian covering, then function will be derivative of this exponent of x minus 1 and so on. So you get exactly this example with gamma function. And in general, if you consider such situations, the set of critical values function universal cover will be finite union of zeros of one form, which usually are finitely many, here it's only one, of torsos of some finitely generated subgroup. You shift by all possible periods of your one form along first integer homology classes. In this example, periods form group 2 pi I integers, so that exactly explains this behavior for gamma function. Yeah, so we proved that we get a gamma equivalent resurgent package with infinitely many critical values. In fact, we didn't really prove that you get analytic continuation of Barré transform. We formulate in terms of Riemann-Hilbert problem. I think it's actually a better formulation. And conjecturally, it implies a traditional formulation with Barré transform and integrals by Écalle. But also it remedies certain potential analytic difficulties. For example, in this Écalle formulation, when we consider the straight ray, it can be will be closed very many times to some singularities, and it's not clear whether the integral will be absolutely convergent at all. Yeah, so there are unpleasant analytic difficulties, especially when lattice became everywhere dense. And in our approach, we have a way to avoid these difficulties. And in the special case when lattice lies in kind of Gaussian integers or Gaussian rationals, both real and imaginary parts are rational numbers, then if you consider generating series in an appropriate state for Stokes indices in any rational angle sector, you get rational matrix valued function which you can calculate. Yeah, so it's everything is kind of completely calculable and under control, and there is a whole story about fault crossing formulas which I don't want to talk about today. And there is something new series which we called holomorphic, some misprint Markov series, which we developed, and it's behind all this result. Actually, I gave some talks about this, but I will not do it now. So now I go to next level of complexity. It's called Fadeev quantum dialograph. It's again some examples which should be in a future textbooks, but it's not yet in textbooks. So what is it? We fix some complex number. Actually, it should be complex 0 and 1. Sorry, it's again some misprint. And consider the following expression in H bar. It will be not a form of series, power series, but what's called expression. Yeah. So whatever it means. So take exponent 1 over H bar times the logarithm of x, the logarithm of sum of x n over n squared. It's a multi-valued function. If x is less than 1, it's convergent, but if x is bigger than 1, you choose one of branches. Plus at 1/2 of log 1 minus x, it's again multi-valued, but the rest it will be completely one-valued. I consider series in odd powers of H bar and multiply by some essentially Bernoulli numbers, values of zeta, Riemann zeta negative integers, and multiply by some rational functions which are even derivative, a logarithmic derivative function x over 1 minus x. Whatever it means. Yeah, so it's some pretty explicit expression. Nice, it's actually asymptotic expansion of what's called Fadeev quantum dialogh, which is actual meromorphic function. And it satisfies the following Q-difference equation in variable x. So if you multiply x by exponent of H bar, then and multiply by 1 minus x, you get original function. Yeah, so you get some nice canonical object. I throw away this dialog from logarithm of these things, and I get exponent of some form power series in H bar, And you get certain series with coefficients are some pretty complicated rational functions with poles at 1. Yeah, so you get infinite sequence of rational functions. I calculate, I don't know, 1,000 of them. It takes some time, but it's doable. And the claims the following: fix is number x, which is, oh, sorry, again, misprint. It should be not negative numbers and not 1. Then we'll have a resurgent package with a singularity set is a rank 2 lattice. It's generated by now 2 pi I square z, no longer 2 pi I, and 2 pi I times logarithm, because logarithm is well defined to 2 pi, it's naturally well defined. So you get a singularity set, and like for Stirling series, you get absolutely the same behavior. All form power series are the same at all points. You have just one series and repeat it everywhere. And the whole picture invariant under shift by this rank 2 lattice. And resurgence implies the asymptotics because again you have 2 closest singularities which contribute. And then you get the same, the following formula. Again, you consider normalized this things multiplied by 2 pi log x to power k, guys, and you get the things. And if you replace this r tilde by s tilde, you get exactly the same relation as for Stirling series. And since Stirling series it's limiting case of the story. Yeah, so you have kind of one parameter family of resurgence packages. It depends on variable x, and it's called parametric resurgence. Yeah, so it's kind of I think this the best example of this parametric resurgence when you have infinitely many singularities. And there is a challenge. Up to now, we don't have interpretation in terms of exponential interval. So we get this, again, when there is, can describe all Stokes coefficients, you get a bunch of zeros, ones, and minus ones. Very easy to understand, but what is it? Topology of Lefschetz symbols and what and manifold of which dimension, I have really no idea. Yeah, so it's really challenge here to find topological model for this. Some integral of a certain dimension, doesn't matter which produces guys. So, and the last part of my talk will be devoted to kind of a bit generalization of this quantum dialogue and a more general story related to quantum Chern-Simons theory and finite number sums. So I'll change completely the gears and recall you what is quantum Chern-Simons theory. First of all, what is Chern-Simons theory? You start with compact-oriented C-infinity manifold of real dimension 3. Now I have some infinite dimensional complex variety, which I sort of treat as an infinite dimensional complex vector space. Let's say I consider one forms on your manifold with values in SL2C, in C3. So it's infinite dimensional vector space, and it has a function which given by integral of, if you get form alpha A, you take trace AdA over 2 plus A cube over 3. It's usual Chern-Simons section. If you interpret A as a connection, you take trace of it, integrate, and you get certain cubic polynomial, let's say, in infinitely many variables. And I would even say that cubic polynomial is rational coefficients. Whatever it means, because you see as coefficients 1 over 2 and 1 over 3 here. Yeah, so you get this infinite dimensional break variety, what to say. This cubic polynomials has huge group of symmetry. It's come from gauge symmetry. You can make quotient by the group G0, which is connected components of the of identity of the complexified gauge group. We consider all possible C-infinity maps from NQ to SL2C. It's infinite dimensional complex Lie group, and you can consider group connected components is Z, but you consider just and components and divide by this, the action will be preserved. One can act by gauge transformation which are not in the connecting points of identity. And then you add to this channel sign, it will not preserve channel sign function, it adds to its 2 pi I square times z. Or you can say that derivative of this function will be well defined if you mod out by even the larger group. Yeah, so we can try to see that we have like algebraic manifold x prime divided by z, on which you have one form, and we take abelian cover, which happens again to be algebraic variety, and then critical points are flat connections. Usually they are finitely many. And yeah, in fact, this is a little bit. I say that they're finitely many, but it's there's a little problem with stabilizers. Yeah, for example, have trivial connection, it has singular point because it has some stabilizer. So, and if you kill stabilizers, then isolated flat connection will be okay, but trivial connection form no, trivial connection will be okay, but isolated form finite dimensional manifolds if you change it to the gauge group. Okay, yeah, so there are little details, but I'll skip them here. So the critical values. The critical values are finitely many arithmetic series with a step 2 pi I square. It's like, not 2 pi I, but 2 pi I square. And the whole story is invariant under the shift, so you get finitely many divergent series. The central factor is equivalent under the shift by 2 pi I square z. So, how to make this whole resorption package? So there is some kind of like physics perspective. You think about this infinite dimensional integrals, and the divergent series is a perturbation theory in field theory, and it's topological field theory, and mathematically formulated well kind of how to make sense of all finite diagrams and so on in early 90s by Axel Orton-Zingel and independently by myself. But it's kind of theoretical procedures. It's not, nobody ever tried to do this actual calculations. It's more high dimensional integrals, finite dimensional integrals to do. And what are Stokes indices? Again, one can imagine like counting gradient lines for real part of action, and it's reduced to something called Kapustin-Witten equation on M3 cross R, because the gradient maps to R to space of connection, so altogether we get things depending on 4 variables, and we get boundary flat conditions at M3 plus minus infinity. Yeah, I think mathematically it's very, very challenging, and there are huge analytic issues with the compactness of the space of solutions. Yeah, so it's kind of more, we have some definition, but not actual way to do things. Yeah, but with this channel 7 series, the whole story actually started in 80s at Witten, but yeah, actually several people proposed that one should study quantum channel 7 theory, but Ed Witten came through with the answer. He proposed a formula for the partition function for the unitary channel 7 theory, the integratable space of unitary connections. It's some kind of like locus of infinite dimension, and you do it in terms of representation of quantum groups at root of 1. So the Planck constant is quantized because its channel sign sectional portion is defined up to 2 pi square and divide by h bar. So you look at h bar should be 2 pi I divided over some integer, which is called level, and then the expression is well defined. Otherwise, it's not well defined. So you get things. This interest depends only for kind of quantized value of h bar, and this cycle of integration is not the Lefschetz symbols, but one can argue that it's by kind of gradient flow should be equal to finite linear combination of Lefschetz symbols. So one should, that was kind of dream for many years. Now, what I'll tell you is there's no way to formulate things like what are divergent series and what are Stokes indices more or less rigorously mathematically. So first of all, one should really follow this hints from unitary quantum channel Simons. when we transform it in terms of this quantum groups at root of 1, one can go to projection to third along a node, so on, and one could reduce to some CGC with some R matrices, and essentially, after making some additional triangulation or something like this, one can rewrite the partition function in terms of some finite num sums. So what are finite num sums? You imagine you get just bunch of discrete variables going from 0 to n minus 1. You consider q is a primitive root of 1 which is very close to 1, the closest one on the left, exponent 2 pi over n. Then consider q factorials like this, and we take product of q factorials times q times quadratic form, maybe some linear part, I just omitted here, and take some things of all Li's. It depends on some integer symmetric metrics, maybe the rational coefficients. Yeah, so it's some expressions like this, some kind of hypergeometric type, Q hypergeometric type sums, roughly speaking. And with such thing, we can associate multi-valued function on complex variables. Products, you replace factorials by Q factorials by logarithms because it's asymptotic behavior of them. And this quadratic form replaced by quadratic form and logarithm. You get multi-valued quadratic, multi-valued function on torus, and one can see that critical points and values correspond to those in Chen-Simons series. So it's some kind of finite dimensional replacement of integral of the space of connections and this multi-valued function. So what prediction for this perturbation theory? So we should integrate this f0, which is sum of the logarithms, and plus quadratic form of logarithms, and with the logarithm we replace by this series which you see before in this formal Faddeev of the logarithm, h bar, values of zeta, and then derivatives of log of 1 minus x. Yeah, essentially replace the logarithm with quantum logarithms, and we try to integrate this guy near critical point. Near critical point, again, you use usual Feynman rules, so weak formulas. And it's some algebraic procedure. For example, if my sum is one-dimensional, which is already a huge class of examples, one can calculate exactly perturbation theory up to order of h to 1000, say. Yeah, it's really enormous for resurgent purposes. So you get explicit answer, and coefficients will be some algebraic numbers, and you get a huge collection of algebraic numbers. Yeah, and what are Stokes indices? Stokes synthesis, it's still kind of under development. We have kind of general theory with Jan Sobelman that should count some pseudo-holomorphic disks in a complex symplectic torus with some certain boundary conditions. It's a holomorphic float theory. It's some generalization of holomorphic Morse-Novikov theory, and presumably it can be also make essentially effective and combinatorial, at least for this dialogue from examples. What Stokes synthesis should we expect? It's really interesting. I will explain you some concrete example, which is a bit special, or we can say degenerate, but the nice point one can really go to the very end. In this example, I will start describing this form power series package. There are two form power series in these things, and then the rest will be by shifts by multiple of 2 pi I square. One series is oh, sorry, it's again misprint. There was some E missing here. Yeah, it's a little bit like num sum, but maybe with no, it's essentially num sum, kind of num sum, finite num sum. But now consider exponent of h bar as formal, h bar as a formal variable, and you get this infinite guy. And you see when h bar goes to 0, then the high terms will vanish with higher order in h bar equal to 0, so one can make formal power series expansion. And you get easily some series with infinitely many terms with rational coefficients. Again, you calculate this 1000 terms, it's not a big deal. It's one series, and another series is just constant, 2 pi I square root of 2 multiplied by 1, h bar to the power 0. It's like Gaussian integral. For people who know the subject, A0 should be thought as Asuki series, expansion of quantum channel assignments a trivial connection, and another guy, its expansion some non-trivial connection, and manifold should be something like Seifert manifold. So this channel assignments function will be a rational multiple of 2 pi square. So we replace this series. So it will be singularities in the plane. Yeah, here it will be not exactly 2 pi square but divided by 2. So I place my series I0 formal at arithmetic progression, essentially the arithmetic progression divided by 2, and I1 by shifted arithmetic progression, shifted by this number 2 pi square of 48. Or I can say these numbers rho k, which are all non-zero numbers, which pi square over 12 times k, the k is 1 model 24. Yeah, so I get just two arithmetic progression. And the only non-trivial Stokes indices in the situations are a very stupid one. They connect points when you place I0 formal, the points when you place I1 formal. And the whole story is invariant on the shift. So you get Stokes indices depends essentially on this k equal to 1 modulo 24. And if you make generating series, you divide by absolute value, then I get L function, some object in algebraic geometry, or called quantum modular form, so whatever. You can see the L function of certain diagonal Artin representation of Galois group of Q bar over Q, and it's somehow related to some nice series discovered by Ramanujan, and it's Henri Cohen who realized that it's L function. And the corresponding automorphic form is not holomorphic modular form, but mass form is eigenvalue of Laplacian 1/4, whatever it means. Yeah, so one can write the series. It's there are many ways to write it. It's ratio zeta function of two number fields, like quartic and extension, quadratic expansion, and just certain series, some small coefficients growing very, very slow. So this. My postdoc Veronica Fantini, we make some calculation last month, and we discover the following. This so we first try to find this asymptotic, but like I said, this asymptotic controls by nearby zeros, but here one get exact formula. So the nth coefficients of this series Cn, which we construct for this num sum, is equal to whatever n minus factorial square root of 2, and this sum of these integers tk, which are Stokes coefficients, divided by this rho k. So essentially get values of zeta function or L function at positive integers, and divided by power of 2 pi. And then also you can get explicit formula for Barrelier summation. It's infinite sum, and here you get some nice expression. If you look what is it, it's really bizarre function. It's called exponential integral in proper sense, or incomplete gamma function, and I communicated with Don Zagier. I showed him this formula and related things, and he said that he never seen it's a number theory, but it can appear in this way. And how it's related to this what to be quantum channel series of the Simons group for the compact group integral of unitary connection. One can argue by analogy with real life examples that partition function should be value of this guy, which is essentially the same series you should draw before, the q is exponent of 2 pi I tau. Yeah. But now you can evaluate it 1 over n, you get finite num sum, make this simple factor, and the claim is this sequence of numbers which we get here. It's actually values of at quantized Planck constant of this Barrelier summation plus some extra term, and extra term it's actually a1 and shifted point. You see that you get kind of really very simple example of all this resurgence. So resurgence, it's very, very much abelian. It's essentially like upper block, strictly upper block triangular matrix of size of very infinite size, and all invariant under the whole local system is invariant under shift by 2 pi square. And then if you go to the quotient, you get representation of fundamental group of C star minus just two numbers, 1 and exponent 2 pi 24, come from this position of points when put first and second series, to JL infinity with integer coefficients, and JL infinity, it's actually 2 copies of Z, because I have 2 arithmetic progressions. And there are some kind of pretty dumb mononomial matrices, but